Okay, this next presentation, the work was done by Dr. Chad Goodnight, who's with HDR now, and it was supervised by me. Chad was with us at WSP at the time, and so I'm presenting on his behalf today. So I'd like just to recognize that Chad did this work. And this follows on to what I showed you before, that we've got the single degree of freedom systems. We looked at quite a few of, and then more detailed looks at actual bridge designs. That'll come in the next presentation. So for the single degree of freedom study, we looked at just a group of columns, and we didn't try to optimize these. We just looked at, say a typical column, maybe a 6-foot diameter column. In this case, we chose fixed top and bottom. We could have chose fixed at one end, but this was just for relative comparisons. We looked at 3 typical axial load ratios of the axial load over F prime CAG of 8% of the concrete strength, 12%, 16%, 3 aspect ratios of this column that typically keep it in the flexurally controlled range, 3 longitudinal steel ratios that are typical, say 1% up to 2%, 2 transverse steel ratios that are more down around the minimums. You can go higher if you need to, of 0.7% and 1%. And then the seismic weight was set at a little more than the column axial load to recognize you may have more, say if you've got sliding bearings at the end, you've got more tributary seismic inertial mass than you have gravity load on the column. We looked at 13 cities in the U.S., across the U.S., and we used the 2014 100-year and 1,000-year hazard from USGS, even though, at the time, and even right now, we're still using older USGS formally in the AASHTO documents, but we knew we were moving to more current. And so in those risk-targeted motions that I mentioned earlier, those are now based on the 2018 USGS hazards. But that's coming in the future, not here today. So here are the cities going from, sort of low, sort of East Coast. It sort of bounces around here, but different seismic hazard. These are not really, they're kind of arranged in seismic design category, but that 1 second 1,000-year return period you can see there in the middle column. You've got Charleston, South Carolina, which has a fairly high seismic hazard. New York, much lower. Boston, lower. Knoxville, relatively high, surprisingly. These are on site class D. Paducah, Kentucky, which is starting to get into that New Madrid area of the central U.S., as is in St. Louis, and then Helena, Montana is in kind of the periphery of the Yellowstone hotspot, so a little higher seismic. Salt Lake City and the Wasatch Range and fault is pretty high. LA and San Francisco, obviously. Seattle, Cascadia subduction zone. Juneau, Alaska, with its seismic zones in that area, and then New Madrid itself. This last one's kind of right on the bullseye. And so on the right-hand curve shows comparisons of the 1,000-year, say New Madrid versus San Francisco, so central U.S., western U.S. Those are the blue and the purple. The 2 top curves are the 975 or 1,000-year event acceleration response spectra for the 2014. And then for those same 2 sites, New Madrid and San Francisco, the 100-year. And you can see here kind of a relative difference where the 100-year and the 1,000-year in San Francisco are, maybe it's a little over 2 times generally. And then in the New Madrid area, the difference between the 100 and the 1,000 is much greater, maybe a factor of 5 or 6. And this is part of my response to that last question, is that the relative hazard across the country varies a lot in between return periods. And the same is true, so if you're doing a major structure over the Mississippi River, you're probably designing that for a 2,500-year earthquake, not a 1,000-year earthquake, because of some of these changes. Going from 1,000 to 2,500 in that area gets even bigger. So this is the background there, and then this starts to show a series of plots of results for these columns, and you see various combinations at the top. So we got a longitudinal steel 1.5%, transverse 0.7, relatively light, axial load ratio of 0.08, and a aspect ratio of 5. And so the 0.8 is highlighted in red because the next series of graphs, that's the thing that's going to change. And then what you see is a pushover curve here of that column, and then different waypoints, if you want to think about it, on the curve of the limits relative to what that column can experience. So, for example, you see these clusters of blue dots or blue crosses. Those are the 100-year demand. So just start with the simple. That's almost everything's purely elastic here, so it would satisfy the PL3 criteria. PL3 for the steel would be say the green diamond there at about 4 inches, and so you can see all these sites have a 100-year earthquake that would work well in that case. PL3 for the concrete is the red box, just a little bit to the side, still fine for the lower level 100-year earthquake. This design was not, we just picked a column, and it's kind of the way we went through here. It didn't iterate in until we were right at some limit. So this is just, and this is not unusual in bridge design. You don't always take everything out to the limit. But if we look at the limit here, the PL1 for steel, so that's life safety limit for steel, is the blue circle. The PL1 for concrete you don't see here because it's way off to the right there. So steel always controlled relative to PL1 for concrete in this study. So PL2 for concrete is the kind of orange X there at 12 inches. And that's also the current limit that's in the guide spec. So you see the curve stopping at that point, and you could go all the way out to the PL1 for steel. But then if we look at the kind of the largest demands for the 975, the largest purple is right there about 7 inches, and that was for the New Madrid design. And then San Francisco and LA are there about 5 inches. You can see two purple X's concentrated there, so well south of the capacity of this column. And then there's a black circle and a black box that are the direct displacement-based designs for San Francisco and New Madrid. So those would be the demands using those, and we call it direct displacement-based analysis there, since we're not really doing the design, but we're using that method for estimating the inelastic displacement. And you see that those are generally, in some cases, higher than the AASHTO design. We'll come back to that notion. That's an important thing here that came out of this study. If I blow this up, this is the same information. Probably should have jumped to this slide a few minutes ago. This repeats what I just told you. And then if we look at the 12% axial load, everything else being the same, here's that detail. And again, you see kind of the limits for the operational limit for PL1, which steel is controlling. You see the 975 purple demands, the 100-year blue crosses as those demands, the various PL3 limits and PL1 limits. So you can see how in this particular case, the PL3 could control for certain locations in in the New area, because the PL3 concrete limit is right at the where the curve starts to roll over. And that's about where our conventional beam design would be, flexural design, if you use 0.003, is about right, a little beyond that rollover of the curve. And then for the higher axial load, you get a little bit less ductility. The curve has been pulled back to the left, you would expect that, and you see the relative relationships of the PL1 performance levels, those limit states, and the 975 and the 100-year events. And you see now you have a PL3 concrete at the, so 100 level, PL3 elastic concrete controlling for, or nearly controlling. LA and San Francisco just worked there. So, and then if we resort this, you see the 1,000-year versus the PL3 limit, for example. I'm sorry, the 100-year. You see that there are only a few 100-year demands that exceeded the PL3 limits in the whole study. Now, we didn't see any of that in the 3 curves that I showed you here, but there's a curve in the report. There's a curve for each of the 54 combinations that we looked at. And then these were just sorted in ascending order. Likewise, effects of strain limit. I just showed you the axial load ratio, but if we change the strain limits, we change the aspect ratio, that sort of thing, you see the progressive change in what the ductility, displacement ductility limits are here for different columns. And in the highest design category, say a multi-column bent, displacement ductility is limited to 6. So you actually see another, in the highest category in design, SDCD, that ductility limit of 6 would start to control over the strain limits even. And in part, that ductility limit was a judgment call that was added because that's typically what we've seen really dependable performance in the laboratory for. So, yeah, and then effects of transverse and longitudinal steel, sort of the same thing, just progressive increase there. So the columns have been sorted by the higher ductility limits. And then, in this case, I wanted to kind of put a little more color on this estimation of inelastic displacements from elastic analysis and loop back to that direct displacement-based design family of curves that we saw on the first slide. So currently, in AASHTO family of documents, so LRFD, in the guide spec, we use this coefficient method that we do an elastic analysis, and then depending on the period of the structure relative to the corner of the spectrum, where you go from constant acceleration to the velocity control region where you have a descending branch. So if you're to the right by 125%, that's 1.25 in the graph at the bottom there, regardless of your ductility demand, the AASHTO would tell you that the displacement of the inelastic structure is equal to that of the elastic structure. And if you are less than that period, the 1.25 of the corner spectrum, then you have amplification in the short period range. And that comes from the observation that short period structures tend to have much higher inelastic demands, but they have smaller displacement, so they still work. This is purely a curve fit, beat to fit, paint to match sort of thing. Whereas my contractor said, I don't know that we did that here, heat to red, beat to fit, paint to match. The complete different way of doing this is the direct displacement-based analysis, also goes by the name capacity spectrum or substitute structure method, and that is, you can look at a family of response spectra. You can plot response spectra now as spectral acceleration, and instead of period, spectral displacement. And it's just a matter of reparameterizing the equations. And so the typical design spectrum is 5%. But if we look at the substitute structure with a secant stiffness at the maximum displacement point and greater than 5% damping because of the hysteretic response, we see a reduction then in the maximum displacement, even though we're using a secant stiffness, which makes the structure more flexible, which typically would make you have a higher displacement. And so this is just a different method, a better method than the purely empirical one to estimating the inelastic response from an elastic analysis. So we looked at these two in our method here. And so to summarize these, the AASHTO empirical method is based on purely a yield level stiffness, initial stiffness, and constant 5% initial stiffness proportional damping. So the analyses that were done, and these go back to the early 1960s and Nathan Newmark and those guys. This 5% initial stiffness, we believe, is too high, initial stiffness proportional damping. Because once things start to yield, and this is the conceptually sentence at the bottom, as a full plastic mechanism starts, you cease to have these local displacements in the other elements, and all the displacements are at the mechanism level. And so since we're coming up with the damping based on that mechanism, it's kind of double dipping to continue to count 5% initial stiffness damping in the rest of the structure. So the direct displacement based design uses equivalent secant stiffness, and now the new thing on this slide that I didn't mention on the other is that we're using tangent stiffness proportional viscous damping. So the procedure has built into it this tangent stiffness, which means that as you get to full mechanism, the tangent is 0. And so the damping drops way down. Well, when you do that, the displacement should get bigger, right? Well, we'll see how this works. And then the hysteretic damping, at that point, the full mechanism level is what's actually producing the, quote, damping that we're going to take the equivalent elastic damping coefficient from. And so if we go back to this kind of the middle column, same family that we looked at earlier with the 12% axial load, and now you've seen all these other dots on this curve before. Now I want you to look at the black circle and the black square. Those are direct displacement based analysis of San Francisco. That's the black circle. New Madrid is the black square. Their strain limits, for example, depending if you're using these for PL1, you see that probably works for San Francisco, but you're getting into an unconservative range with the New Madrid. And so the AASHTO demand of New Madrid, so we're looking at the right side of this plot. You see the purple X for New Madrid. That's what AASHTO would tell you right now the displacement is. The direct displacement based analysis would tell you that the demand is that black square. Well, there's a whole lot of difference there, which says that we may be unconservative in some of our estimations, and so we need to improve this. And right now there is a project out there to try to do just this. And you see the same relative non-conservatism with the San Francisco estimates, although it's not quite as big. So the non-conservatism is higher for higher ductility demands. And so if you're right at the yield point, the two methods are going to give you the same answer. If you've got a ductility of 2, the two methods don't give you that much difference. But as you get up to 4 and 5, because you're counting on this higher damping with the AASHTO method than with direct displacement-based design, you're going to see bigger differences in the predicted displacements. Fortunately, probably a lot of our bridges, say if you got a 2-span overcrossing locked into the soil and abutment, The soil provides a lot of damping. You're really not cranking columns over at a ductility of 6. That's the good news. But this is something that needs to be looked at. And so in summary, we've looked at, in these guideline limits, we've looked at sort of the impact of the performance levels on typical column designs, and then looked at this impact of the inelastic approximation method, which I would venture to guess most people, when they're using the spec, they don't even realize they're doing this. It's sort of hidden from sight, but it's a quantum leap of faith that you can predict this inelastic displacement. So with that, are there questions about this portion of it? And if you want to loop back even, I think you had a question before, I'll come back to you, Saki.
So I have a question that is how do you generate the pushover curves?
Generate which curves? The pushover curves? Just using the typical extract type properties, and then pushover with SAP or typical programs. Mm-hmm.
How do you manage to apply the axial load on this node because the top nodes are vacant? There is no load transfer to be qualified.
No, the axial load, it's just a single degree of freedom, so the axial load stays there. It's not going anywhere else.
So you just, you want bending or roller.
Yeah, you have a roller there that you push over, and the axial load stays there. Yeah. It's no rotation at the top, and it was a concentrated hinge model, not a pattern model. Yeah. So okay.
I was just wondering, you mentioned the tangent stiffness, and the other papers out there about control brothers, overestimating those. Is that related to nonlinear time history analysis that you did to come up with equivalent displacements? Where does that go into this procedure? I'm specifically curious about where you used it.
Okay, so the question is, did we do nonlinear time history analysis to estimate these displacements? And in this project, we did not. There are a family of curves that have already been developed based on the tangent stiffness from number of time history analysis that were done years ago by Priestley and Dr. Kowalski and others, I think. And so we were using those for this purpose. So it's sort of an intermediate step as opposed to doing a bunch of nonlinear time history analysis where, frankly, you didn't have the fee for that in this project. So, yeah. So, other questions? Yes.
Can you please go back to the table of SD1 columns, SD1 columns depending on the recurrent period?
This came, so the question is, how do we get the SD1, the 1 second spectral acceleration for the 100-year value? Or 975. How do we get the 1,000-year? These came straight from USGS for the site class and the latitude, longitude of those sites. So this is from the U.S. Geologic Survey.
So what you are saying here, that 975 years values are almost 5 times or 3 times of what we are saying for the 100-year period, right?
That's right.
So my question is, I'm just thinking about it, that once we are increasing the load to 5 times level, and then we are again doing a design which is again pulling it back to a lower level. So why will somebody go for it? What is the justification for a 1,000-year design? That is my question. Why are we going for 1,000 years at all? Because I do not know where it is specified. Most of the codes mention that the life cycle will be 100 years, 150 years, 200 years. So what is the basis for 975?
So the 975 was determined many years ago with AASHTO, where we had, for example, historically we've been designing for 500 years. We knew that there were parts of the country where the earthquake hazard for 500 years was very much less than what some of these sites could see, say in New Madrid, Charleston, South Carolina. So there was, at one point, an NCHR pre-project where we proposed 2,500 years as the design, and that was thought to be too big. This kind of became a judgment call. 1,000 years corresponds to, and when you talk about return periods versus design life of a structure, it's not quite illuminating what you're doing. It's better, really, to talk about it in terms of the probability of exceedance in a certain number of years. So the 1,000-year event has a 7% chance of exceedance in 75 years. 75 years being the AASHTO design life of a bridge. That for other load cases, we're designing for 75-year life. So it was then judged that, well, if we designed seismically for 7% chance of exceedance, that would be a reasonable thing, then that corresponds to the 1,000-year. So that was set in place for ordinary bridges. Now, when you look at like Cape Girardeau suspension bridge or cable stay, you would probably want something with a much lower probability of exceedance in the 75-year life. So you might then use, say, 20, this is what's typically been done, use 2,500-year design hazard.